The next big topic we're going to discuss as we lead up to calculus is the idea of the area problem. And I took a couple of easy sequences to kind of get our feet wet to understand what's going on with this before we actually get to the area problem. So in the holiday song 12 Days of Christmas, they're actually giving gifts to their true love. So when the 12 days are over, there's going to be a lot of gifts that are given. So if I add all of those gifts up, I will get the total number of gifts. But that's 12 things to add. Not hard, not difficult, but there are a lot of things there. Now there are some easier ways to tackle this instead of just going to a calculator or things like that. We can pick out some tens. 7 and 3 add up to 10. 6 and 4 add up to another 10. So I've got 1, 2, 3, 4, 5, 10. So I'm already up to 50, 61, 73. It looks like we're up to about 78 gifts. Not unmanageable, but I want to take a look at a little harder example. Carl Friedrich Gauss, he was a French mathematician, was given this problem, the stories go he was given this problem when he was in elementary school. He was a very advanced mathematical thinker, and his elementary teacher wanted to keep him occupied. So gave him a problem like this and said, let's add the numbers from 1 to 100. And he was done like that. And the teacher was shocked and said, well, what if I asked you to do 1 to 1,000? And he came up with this system that made this easier. Now, at first thought, this is the task that you're faced with. All right, I need to add the things from 1 to 100. It's going to take a while, but I can do it. What Gauss said is, what if I instead wanted to add the numbers the other way around? And he said, actually, I'm going to do both. Because if I add them this way, or I add them the other way, each time I get 101. And since there's 100 numbers here, I actually get 101 100 times. 101 100 times. The only problem is I did it twice. So I'm just going to cut this in half, and that's the only calculation I need to do. So half of 100 is 50. 50 times 101, that's a much easier calculation for me to do. 5,050. When the problem was changed to 1,000, all that changed was this calculation. This became 1,000. This became 1,001. And all of a sudden we have this pattern that any type of problem like this became very, very simple for Gauss to do. So let's take that into something that we can use. I've got some summation formulas down here that are similar to this. Some things that we come across regularly. Like if I wanted to add up a bunch of constants, I just need to know how many of them. And I take n times that constant. If there's 20 times, I take 10 times 20. If 10 is 5 times, I take 10 times 5. If I'm going to add up 25 twos, 25 times 2 is 50. That's how multiplication was defined. But what if I wanted to add up a sequence of numbers, starting at 1, and then 2, and then 3, and then 4, like Gauss did here? This is the formula we would use. The number of items plus 1, cut in half. That's where he came up with that formula. Sometimes we'll see squared items. If I want to add up squared items, this is the summation formula we would use. Even if we have cubed terms, we have a summation formula that shortens this process. And there are more, but these are the common ones that we're going to deal with when we start talking about the area problem. So I did a couple of examples for you. We have a couple that we need to finish. But I wanted to add all the numbers from 1 to 200. Well, these are the numbers listed out, but this is what it would look like. I have a formula for this, n times n plus 1 divided by 2. I just need to plug in the 200 here and here and actually do that calculation. I get 20,100. Here I've got a squared one. I'm going from 1 to 50, so 1 squared, 2 squared, 3 squared, all the way up to 50 squared. It's going to take me a while to do it by hand, but if I use the squared term summation formula, so I'm going to go back here and look at this, I'm going to replace n with 50. So if I plug a 50 in here, a 50 in here, and a 50 in there, that calculation will tell me what the sum of the first 50 squared terms are. So I'm actually going to take 50 times 51 times 101 and divide that number by 60, a calculation that you can do. So let's dive in just a little bit deeper. Okay, now I have kind of a combination of things going on here. I want to add up the numbers from 1 to n. They didn't give me an ending point. And this is what's going to happen. I'm going to plug in a 1, then I'm going to plug in a 2, and I'm going to plug in a 3 until I get to n. So this is what it would look like multiplied out, and eventually I get to n plus 2, that last term, divided by n squared. So I'm going to tear this apart a little bit, some things that do change and some things that don't change. The first thing that I notice is this n squared isn't going to change. That shows up in every one of these. So I'm just going to pull that out front for right now and focus on what's going on in here. Now there's two parts to this. There's a 2 and there's an I. That 2 is consistently there as well. So when I look at this, it's two different sums. It's the sum of all the i's over and over and over again. And it's the sum of 2, which happens to be a constant. So I'm going to use my two summation formulas that show up right here. The sum of I, which is right here, it says n times n plus 1 over 2. So for this piece, I get n times n plus 1 over 2. For this piece right here, I'm always adding 2's. 2 is a constant. So I'm going to add up 2 n times in this case. So I get 2 times n. Now it's going to make sense to get common denominators, put these things together, and then put this back in. So I'm going to start doing some algebra here. I'm going to distribute my n. I'm going to get a common denominator here. So I still have that 1 over n squared. When I multiply that n in, I get n squared plus n over 2. And I'm going to get that common denominator of 2. So this actually becomes a 4n over 2. Now I can put those together. So I have n squared plus n plus 4n, so n squared plus 5n over 2. And now I'm going to put my n squared back in, my constant that's been there. So I end up with n squared plus 5n over 2n squared. So I can do some algebra here, I can do some simplifying, or I can take what I've learned about the sequence limits, divide everybody in here by n squared, and I get n squared over n squared, 5n over n squared, 2n squared over n squared. This is going to still have an n in it, so it's going to go away. I get 1 on top, I get a 2 on the bottom. This particular sequence is going to give me 1/2 eventually. Now, if they ask you to do it numerically, and they may, when I get to this point right here, I've essentially figured this out. I just need to know what n is. I assumed n goes to a very, very big number, but this particular example said I want to find the sum, and it gave me some n numbers to plug in. They wanted to plug in a 10. So I can plug in 10 right here. They said, what if it's 100? I can plug my 100 in for n. Plug in 1,000. Plug in 10,000. But what you're going to find, which we've done numerically in the past, is the bigger this number gets, the closer it gets to infinity, this is going to actually approach 1/2. So numerically, plug in their numbers. If they don't give you the numbers, kind of like they did earlier, I'm going to assume those go to infinity. So we've got one final example here to take a look at. We're looking at the limit of this sequence of numbers as n approaches infinity. They did not give me a target. They didn't say 100 terms or 1,000 terms. They just said, in general, what's going to happen to this sequence. So here's the sequence that we're dealing with right here. 1 to n, 1 plus I over n squared times 1 over n. So there's some algebra to do, obviously, first for this sequence. This summation is still going to be here all the way through. I'm going to start first by squaring this. And actually, before I square it, I'm going to get a common denominator in here. N over n plus I over n, and I'm supposed to square that. So I've got n plus I over n squared times this 1 over n. So I'm going to square this first because my powers come before my multiplication. My summation symbol hasn't gone anywhere. It's still out front. But I've got to multiply this. So I've got foiling to do on top. And this n to put in. When I multiply this n into this thing and I multiply the 1 in, all that's going to change is the denominator. So now the denominator is going to be a cubed instead of a squared. And my summation symbol is still out here. I'll get to that. Okay? Now I'm going to break this into its pieces. Okay? I've got some i's in here, so I need to pull out the things that aren't going to affect it. First obvious thing that I'm going to take out is this n cubed. Okay? That n cubed can go way out in front because it's not going to change. Whatever n is, it's always going to be 1 over n cubed out front. And that leaves me with the summation of n squared plus 2ni plus I squared. Now each one of those has a summation, so we have to think of them piece by piece. And again, that 1 over n cubed is going to stay there. So I have this summation of n squared. Well, that one's fairly straightforward because whatever n is, I'm going to add that up. So that 1 times n squared is just going to become an n squared. There's no i's being plugged in there. Then I'm going to have this 2n times I. So I have a sum the 2n is going to go out front, and I'm going to have this thing to deal with. That's going to actually change each time. The 2n is not going to change. It's always constant. Same thing here. I'll put my n cubed out here. This n squared is never going to change. It's going to be the same thing over and over again. There's just a 1 in front of it. The last piece that we've got is a summation of this I squared. That's another one that I have to do because I is changing each time. So I need to figure out what this looks like. So there's a lot of algebra here just to get us to this limit that we're trying to find. So I had some pieces that were pulled out. And what you're going to notice is eventually I'm going to divide these. Eventually I'm going to divide these. So that kind of goes back to our strategy of dividing everything by the largest power, and seeing what's left. So I have a formula for a constant, n squared times that constant formula. It's a constant times n, so 1 times n is that sum right there. And then I have a summation for I. That's the one that says n times n plus 1 divided by 2. And then I also have this one for n squared, or I squared, excuse me. It says I'm going to have an n plus 1, a 2n plus 1, all over 6. So there's a lot of algebra left in here. So I'm going to fast forward some of those algebra skills. You can distribute and distribute. You can FOIL and distribute. You can do all those things. But we end up right here with a 14n cubed, a 9n squared, and an n all over a 6n cubed. Notice the 6 comes from here. I can get a common denominator. This is where I end up. Now we're going to take that strategy. Now that I have what this sum is, I have a formula for all these different pieces. I did my algebra skills. Now I can divide everything by the largest power of n. It looks like we're dealing with an n cubed. So I'll take the 14n cubed and divide it by n cubed, the 9n squared divided by n cubed, the n divided by n cubed, and the 6n cubed divided by n cubed. Most of this goes away. I'm going to have an n left here, actually an n squared. It's going to go to 0 as this gets big. I'm going to have an n left on the bottom. Yes, I still have a 9 on top, but that n on the bottom is going to make this go to 0. The only ones that leave me with any kind of numbers is I get a 14 on top and a 6 on the bottom. So, if I did it numerically, if I did it graphically, I'm going to find that this sequence of numbers, starting at 1 and going to n, and letting n go on forever, is eventually going to end up at 7 halves. That's the limit as n approaches infinity. And again, we're trying to lay the groundwork here with these summation notations to get ready for that area problem, which is going to use these to help us out.